Good day. Today I'm going to be talking about isomorphism. In particular, an isomorphism is a one-to-one onto homomorphism. And it sounds sexual, but it really isn't. Or perhaps if it was, it would be more interesting. By one-to-one, I also mean injective. They mean the same thing. By onto, I also mean surjective. They mean the same thing. By homomorphism, I also mean operation preserving. They mean the same thing. Before illustrating what an isomorphism is between the integers under addition and the integers under addition, I'd like to illustrate what an isomorphism is not. In other words, when asked to prove an isomorphism, 99 times out of 100, you are asked to come up with the mapping on your own, which is an isomorphism. And this is usually the toughest part of these proofs. So it's good to have an intuitive feel for what is not an isomorphism between two groups. So I'll be looking at things that are not isomorphisms between the integers under addition and the integers under addition. And then I'll conclude with the actual proof of an isomorphism between the group of integers under addition and a group of integers under addition. Let's consider a mapping first that is not one-to-one. For example, if I was going to map, let's say, one set to the other set, I'll call this mapping F. And I'll define F as f of x equals x squared. So there's my mapping. So is this an isomorphism? Well, the answer is no. Why not? Well, for one, it fails to be one-to-one. Why does it fail to be one-to-one? Well, you see, if I were to graph this function, f of x equals x squared looks like this. And two functions are one-to-one if whenever f of x equals f of y, we have x equal y. But here you see I have an x sub 1 here, and I have an x sub 2 here, and they both have the same value of y. So let's say that's 4, and x sub 1 is negative 2, and x sub 2 is positive 2. So you see then in that case that f of negative 2 is equal to f of 2, because 4 equals 4. Remember, f of x equals x squared. But 4 equals 4, but certainly negative 2 does not equal 2. And so it is not one-to-one. So if I was trying to dream up a mapping from the group of integers under addition to the group of integers under addition, f, such that f of x maps every x to x squared, would not be a good mapping to choose. Why? Well, for one, it is not one-to-one. It is not injective. Okay, so yeah, like that didn't work. So let's try another mapping. Let's say I choose to match 3 to some number over, an integer over here. Let's match it to 6. In other words, this time I have a mapping, I'll call it H. And then this time I'll have H takes n to 2n. There's a mapping for you. So every integer over here is mapped to twice that integer over there. Well, this will not establish an isomorphism between the two groups either. And the reason why is because it fails to be onto. You see, for a function to be onto, everything in this image has to have something mapped to it. Say that again. Everything here has to have something mapped to it. And we have things over here that don't have any integers mapped to it. You see, there are integers that are not twice another integer. For example, 3. 3 has nothing mapped to it. The number 3 doesn't have any pre-image under this mapping. And so this fails to be onto. Onto requires that everything in that group that I'm mapping to has something mapped to it. And in this case, this function, the number 3, would not have anything mapped to it. All I need is one number that doesn't have something mapped to it. And that's enough to establish that proof that that mapping will not work in showing an isomorphism. So therefore, we would not pick H as our mapping. Okay, so how about I try something different? This time, I'm going to create a mapping that takes, you know, a number over here and maps it over here, and I'll call this mapping G. And in this case, G of n will map to n plus 1. So like 3 will be mapped to 4. Cool. So you'd think that would work, but in fact this also fails because this is not a homomorphism. This fails the homomorphism property. What do I mean? Well, it's not operation preserving. Even though it seems like it looks like a dang good mapping, it's not operation preserving. What do I mean by that? Well, in order for a function to be operation preserving, I would need G of, let's say, some m plus n to equal G of m plus G of n. Okay? But in this case, if I took something like G of 3 plus 4, well, that would equal, that would be 3 plus 1, or 4, plus 4 plus 1, right? Well, it should be. But actually, this is G of 7, and it doesn't equal that. Why? Because G of 7 is 7 plus 1, which is 8. And here I've got 4 plus 5, which is 9. So which is it? Well, if it's operation preserving, it's got to be this situation where G of m equals m plus n equals G of m plus G of n. In other words, it's got to be equal to 9. But G of 7 doesn't equal 9, it equals 8. And so this function is not operation preserving, and my mapping G also fails to work if I want to establish an isomorphism. This time I'm going to discuss a mapping that does work. I'm going to use a mapping, I'll call it phi. This mapping will work in establishing an isomorphism from the group of integers under addition to the group of integers under addition. I'm going to let phi sub n equal negative n. Alright, let's look at why, and I'll show the proof. So let's say phi sub n equals negative n. And in proper notation, you see phi is a mapping from the group of integers under addition to the group of integers under addition. Such that what? Such that n is taken to negative n. Alright, so the first thing I've got to show is I've got to show a one-to-one. How do I show a one-to-one? Well, I need to show that if phi of m equals phi of n, I need to show that m equals n. Well, if they equal each other, then I must have negative m equals n. Negative n, yeah, because phi of n maps to negative n. Okay, multiplying both sides by negative 1, I must have m equals n. And so, therefore, phi is one-to-one, or injective if you prefer to call it that. Okay, next we'll show onto. And I'll just draw little pictures over here. Just to be clear. Alright, so if m is in z, this is z over here, that's my m, then m will equal some negative n. In that case, n is over here, you see. So negative m is equal to n, and n is in this z right here. In other words, phi of n will equal negative n, but that's just equal to negative of negative m, which is equal to m. So you see, everything over here has something mapped to it, and therefore phi is onto. Okay, last I'm going to show a homomorphism exists. So if I let m and n be integers, then it follows that phi of m plus n will equal, well, that's just negative m plus n, because that's what my mapping does. Now distributing the negative sign, that's negative m plus negative n. And that's phi of m plus phi of n. And therefore, it is operation preserving. It is a homomorphism. So therefore, phi is a homomorphism. And therefore, phi is isomorphism.
Thank you.